Okay, thanks. I'm Huang, and this is Yuhui. Thanks for being here. We are really excited to share our recent work, Dadu-Corki, algorithm architecture co-design for embodied AI-powered robotic manipulation. This is a collaboration between the Institute of Computing Technology, Chinese Academy of Science, and other 3 institutions. Okay, now let's begin. Here's the roadmap for this talk. We'll begin with the motivation behind our work, and then introduce the Corki approach and its core algorithm. Next, we'll cover the system design for real-time control, and then summarize the experiments and the conclusions. So let's begin with the introduction and motivation. We all know how vision language models are great at reasoning and planning, but embodied AI takes that a step further. It brings these models into the real world, actually control the robots. In our work, we are mainly focusing on the vision language action models using robotics manipulation. We know that the embodied AI plan is ambitious, but reality hits hard. There's a key challenge in real-time performance. Since robot actions affect the physical world instantly, so the latency is critical. As shown in the video, some VLE models can keep up. So we need to think about the key question. Why do current large language model-powered robots struggle with real-time demands? And the answer goes through here. Right now, most systems run frame by frame. You can see the cycles that the model predicts an action, the robot moves, sends back a new image, URI to the server. It's intuitive for algorithm developers since they have paired data to train their models, but super slow in practice. And as shown in the diagram on the left, large language model inference, control, and communication stack up, and it's adding latency at every step. And on the right, you can see large language model inference dominates. Even on powerful GPUs, it's the main source of delay and energy use per frame. So now we know that the frame-by-frame vision-centric loop is slow and power-hungry. But we have the insight that high-level planning doesn't need to run as fast as the low-level control. And we also think that the trajectory is a great tool to solve this problem. So we use it to decouple them. Try to run the model less often, speed up control, and hide the delays through the full co-design of algorithm and architecture. Okay, and then that's where our solution comes in, the Corki approach, a paradigm shift in how we design real-time embodied AI. Corki has 3 parts. First, we predict short trajectories, not single actions, means fewer large language model calls. And second, an accelerator handles fast low-level control. And third, communication runs in parallel to high delays. All right, now let's zoom in on the Corki algorithm and how it plans ahead. We move from discrete actions to continuous trajectories. Our baseline robot Flamingo picks one action at a time, like telling the robot to move step by step. And Corki, on the other hand, it predicts a future trajectory at once, and it's covering many steps, speeding things up. It outputs trajectory parameters for each dimension. For example, if we use a cubic function, it will output the coefficients A, B, C, and D. Okay, now we change the paradigm. But fixed lines trajectories aren't great for dynamic environments. To add flexibility, we use early termination. For example, if the model predicts A to F, the robot can stop at E. That gives users some control over how many steps to take, but it still needs manual setup. So we go further with adaptive trajectories. We detect stopping points and let the model decide how far to go based on them. Here we saw some rules to find stopping points. If the robot detects significant changes, it replans the trajectory, and these points often mark the start of interaction with new objects, so replanning helps the system adapt better. And finally, we use closed-loop features. We take random snapshots during execution and send them to the large language model to get the next move. This helps handle changes better. Okay, and next is the Corki hardware and system. It's also critical to make real-time control work. And Yuhui will walk you through this part, please.
Thank you. All right, so let's have a quick review. The Corki algorithm is to predict a trajectory for the robot instead of one small step at a time. If it reduces the LM inference frequency, note that we don't reduce the inference latency. But now, what does the robot do with that trajectory? The high-level plan needs to be converted into low-level physical force, or torques, that actually drive the robot joints. This conversion process is usually handled by an on-robot CPU. For the robot to move smoothly and safely, this control loop has to run very fast, but the calculation in these red blocks are very intensive. A standard CPU consumes long latency to compute the loop. So, to meet real-time control, hardware acceleration is necessary. Our accelerator design is built on several key architectural insights. The first is data reuse. We observe that the computation-intensive blocks like forward kinetics, Jacobian, and maze matrix share many intermediate data. As the figure shows, later stage consume partial results from early ones. For instance, Jacobian computation reduces results from forward kinetics. Our solution is centralized computation. We compute shared values only once. These pre-computed values are then consumed by subsequent blocks, avoiding redundant calculations. Our data flow accelerator further optimizes performance. It employs pipeline execution so that computations for different links can be done in parallel. Another optimization is application-specific approximate computing. We call it ACE. The insight here is that while robotic control run at high frequency, joint angles often change very little each step. This means many control parameters don't change much with small movements. ACE take advantage of this. We reduce all the computed control parameters if the joint angle change is small, and recompute when change is large. Furthermore, different joints have different impact on control parameters like the maze matrix. This is heavily influenced by the robot's shape. Observe joint 2, a middle joint. When it changes by 29 degrees, the robot's overall shape changes significantly. Therefore, its maze matrix changes a lot. In contrast, look at joint 5, an end joint. When it moves by the same 29 degrees, the robot shape changes much less. Thus, the maze matrix shows a very small difference. When the joint angle change decreases, the change in matrix becomes smaller. This figure shows the impact across all 7 joints on the maze matrix. This observation leads to a more intelligent mechanism. We assign different weights to different joints. Middle joints change the robot shape more, so we give them large weights. A small change in a middle joint is more likely to trigger full recomputation than a similar change at the end joint. Putting this all together, our system reduces the end-to-end latency. On the robot side, operations run in parallel. Our dedicated accelerator executes the current trajectory, the camera captures new frame, and the communication model sends this new frame to the server. As the timeline shows, the image upload latency is hidden under robot control. Let's now move on to our evaluation and results. We use RoboFlamingo as our baseline and evaluate on the Kelvin dataset, which are widely used for embodied AI. For hardware, LLM inference is run on a GPU server. The baseline control uses an on-robot CPU, while cookies control use a Xilinx FPGA. We test several cookie variations. Cookie T means predict 9 steps and take T step. Cookie adaptive is our adaptive length version, and cookie software is the software control on CPU. Here are some key metrics. First, let's look at accuracy on scene task. Cookie 5 is the winner. This is because it finds the perfect balance. If the trajectory is too short, the robot is too cautious and doesn't get the full benefit of long-term planning. But if it's too long, the robot can't react to environmental changes in time. On unseen tasks, which are more challenging, Cookie Adaptive outperforms even Cookie 5. Cookie Adaptive wins because it can decide how long the trajectory should be taken. It can execute a long, efficient trajectory when the path is clear, but it can also choose to stop and reply early when it detects a change. Next, we test trajectory quality. This graph shows the mean trajectory error for different systems. On average, Cookie reduced the mean trajectory error by 25% compared to the baseline. Here is a visual example. You can see robot's flamingo trajectory is over the target, while Cookie 5 can track the ground truth. Now let's look at latency and energy. The blue bars represent average latency, and the orange diamonds represent average energy. Cookie can reduce the LLM inference frequency due to predicting longer trajectory and reorganizing the pipeline, so it can reduce the end-to-end latency. Furthermore, we achieve energy reductions. This is important for battery-powered robotic system. So, to summarize why Cookie achieves this result. First, reduce the LLM inference frequency. Trajectory prediction means fewer calls to LLM, and shown by the sparser peaks for Cookie variant. Second, fast control. Third, efficient pipeline. Next, robotic-centric supervision. And last, adaptive mechanism to enhance performance in dynamic environments. Finally, let's draw a conclusion. First, we identify key bottlenecks in current embodied AI pipeline and propose Cookie, an algorithm architecture co-design framework. Cookie reduces LLM inference frequency, accelerates trajectory control, and pipelines communication to high latency. As a result, Cookie paves the way for practical, real-time LLM-powered robots. Thank you for your attention. We have open sourced the software code on the GitHub, and we are happy to answer any questions.